Alright, zeros of a polynomial function. Remember that the degree is equal to the number of solutions that it has to have. So we're going to look at the degree of a few of these. So we're looking for the highest exponent. This one has a 3, so it has degree is 3, which means it has 3 solutions. The second one, you'll notice it has factors, it has parentheses, so when we multiply, we add our exponents together. So this would be 1 plus 2, it would be a degree of 3. 3 solutions. You have to think about if I were to multiply this out, what the highest exponent would actually be. And so x times x squared is x cubed. Letter C. If we were to FOIL it all out, I would not recommend it. It would take you quite a bit of time to answer this question if you did do that. So again, we're going to look at all the exponents and add them together. So 1, 2, and a 3 gives us a 6 degree. 6 solutions. And then this one here, it looks a little bit different because the exponent's on the outside. So if I rewrite this, this says x plus 4 squared, so that means we write it down twice. X minus 1 3 times. And then x plus 4. And so if we multiply all that out, the highest exponent that you would get would be 1, 2, 3, 4, 5, 6. So 6 degree. And this would also have 6 solutions. Alright, distinct zeros means how many x-intercepts you see on a graph. Multiplicity means that the factor occurs more than once. Graphically, you're going to see a bounce if you have an even number, and inflection point if you have an odd number of multiplicity. So let's look at this first one. You're going to let y be 0 or f of x be 0, set each factor to 0, and solve. So here we would have, well, first of all, if we look at the degree, this is a degree of 2, which means it has to have 2 answers or 2 solutions, and they both just happen to be identical. So we would say that it has one distinct 0 at -2, and it has a multiplicity of 2. So if you look at the graph, I just did a rough sketch here. At -2, your graph is going to bounce on the x-axis. Let's look at the next one. Take each factor and set it to 0. And solve each one. So now this one has one distinct 0. We have to have 1, 2, 3 solution, has a degree of 3. 3 solutions, they just happen to all be the same. So we would say that x would equal -2 with a multiplicity of 3. So here's the graph. It's going to go through at -2, but because we have an odd number of multiplicity, we don't get a bounce this time. We get an inflection point. Inflection point means that it changes concavity. It doesn't really give us a maximum or a minimum, but this is an inflection point. And then this one is our bounce. So that's how multiplicity will be showing up in our graphs. All right, let's look at this example here. F of x equals x plus 3, x plus 3, x plus 2, and x plus 1. And I'm going to ask you on your Google form to solve this. I'm going to ask you for the degree or the number of solutions. I'm going to ask you for any multiplicities that exist, and that's going to be what you're going to answer on your Google form. All right? Let's come down here. Imaginary roots cannot be seen graphically. They always come in conjugate pairs. I am going to change this problem just slightly. So on your guided notes, if you could make this a plus, please. So we can't see these graphically, but because they are imaginary, we can only see real ones. And they always come in conjugate pairs, like a pair of shoes. So to solve, Take each factor, set to 0. And we're going to solve those individually. So I'm going to subtract 3 from both sides of the equal sign, subtract 1, and then on this one I'm going to subtract 4. I have to do a little bit more work here. I'm going to square root both sides. So x equals square root of a -4, negative. So it has to have an I in there. And the square root of 4 is 2, so we're looking at positive and negative 2i. Notice that these are conjugates, right? Also notice that our degree, 1, 1, and 2, that gives us a 4th degree. So we have to have 4 solutions, do we? Well, sure, we got 1, 2, and then 3 and 4. So this has 2 real and 2 imaginary, 2i's. So that gives us a total of 4 solutions. All right, here's another one that we're going to look at. We're solving this, and then we'll talk about any multiplicities and so forth. So let's look at this one. If we let's first figure out what the degree is. So we have 2, so we're up to 4, 5. This is a degree of 5, which means that we have to get 5 solutions. Take each factor and set to 0. And then we're going to solve each one. If you look at this first one, it's quadratic. So we need to like factor it or use a quadratic formula to actually figure out what x is. So what would multiply to 4 and add to be -4? Well, -2 and -2. And then we would take each one of those and set it to 0. So x would be 2, x would be 2. So there's 2 answers. They happen to be identical, so that we got a little multiplicity happening here. All right, on this one we're going to add 25, both sides of the equal sign. And then I'm going to have to solve for x by square rooting both sides. And then on this one, I'm going to -3. So do we have 5 solutions? Let's see what we came up with. So we have 1, 2, 3, 4, and 5. So we could say that it has solutions that are x equals 2 with a multiplicity of 2. X equals 5 and x equals -5 from this little plus or minus deal, and x equals -3. It has 4 distinct zeros because it would have a bounce at 2, and then it would go through each one of these points. I'm going to graph that. All right, so here's what the graph would sort of look like here. It's going to go through at -5, at -3. It's going to have this one has a multiplicity at 2, so we're getting a bounce right here. And so that's because of that multiplicity that's happening, an even number multiplicity, and then it goes through at +5. All right, so it has 1, 2, 3, 4 distinct zeros, 4 x-intercepts. This one bounces, so we get like a double root or a multiplicity. All right, don't forget to do your Google form.